In question 3 then, we're starting off with this compound cyclohexane 1,2-diol. So it asks us for the structure. So cyclohexane is a ring of 6, and a diol means 2 OH groups. And 1,2-diol means if one of them is on carbon 1, the other is on carbon 2. Okay, so the whole molecule is a diol because it has 2 OHs. One's on carbon 1, one's on carbon 2. So then we have this proposed experiment which involves prolonged heating of this substance with concentrated sulfuric acid, and it asks us how are we going to achieve this prolonged heating. So you've come across this concept in the context of oxidation of alcohols. That's not what this is, so don't get confused. We're not talking about the same reaction here because we haven't got an oxidizing agent, so we're not oxidizing the alcohol, but we've got the same problem of how do you achieve prolonged heating, and the way we did that was by using reflux. Okay, so it's really important that you recognise that reflux is a method that isn't just used for oxidizing primary alcohols to carboxylic acids. That's where we met it first, but it's used in almost any reaction in which you have to heat some kind of mixture containing organic compounds for a prolonged time, because most organic compounds are quite volatile. So when you heat them for a long time, they will tend to vaporize and just get lost into the atmosphere unless you take steps to prevent that from happening. And that's what reflux does. So you need the word, you need to make sure you use that word, and then you have to draw the equipment. Now drawings are something you need to practice, and the way to do it is to imagine you're drawing a cross section, so a slice right through the middle of the apparatus. So it's not meant to be a drawing of what it looks like from the outside. Because it wants to show the connectivity, it wants to show where the substances can move freely from and to. So we're going to have a flask, and your flask can either be pear-shaped, like that one, or it can be round-bottomed, but not conical. Okay, it's got to be like that, and that's going to need labelling. So pear-shaped flask or round-bottom flask, and that's where your reaction mixture is going to be, in there. You could put anti-bumping granules in there to help it boil, but that's not generally necessary to get the marks. So then in the top of that you have a condenser, and at the heart of the condenser is a tube which opens into the flask there. So it's very important that you leave it open. Don't draw a boundary across there to mark the end of the condenser, because remember, this is not meant to be what it looks like from the outside. This is a cross section, and in the cross section there is open access between the flask and the tube, so you leave it open there. Round the outside of that tube you have this water jacket, which is going to look something like this. Okay, and this whole thing is the condenser. And the idea is that cold water goes in there. And it must go in at the bottom, rise up, and then come out there. If you do it the other way round, it tends to fall downhill and not fill the tube up properly, so it won't work as well. And they want, again, because they're interested in, have you encountered the practicalities of this? So you did this when we did the practical, but you're expected to take away from that, oh yeah, the cold water goes in at the bottom when you do the question. So you need to make sure that there's no gap there. Okay, you need to make sure that the condenser fits snugly into the mouth of the flask. If you leave a gap there, so that you have something that looks, kind of like that, then obviously that's no good, because your vapour is just going to escape out like that. So you've got to draw it carefully to make sure that there is no gap. And at the top, the condenser is open to the air. If it wasn't, so if you had it closed off there, then of course what would happen when you started heating is that the pressure inside would build up and it would at some point explode. So you have to have it open to the air at the top like that. And the idea is that you can boil this stuff in the bottom gently and the vapours will rise up here, but as soon as they hit this wall, which is kept cold by the cold water flowing through there, as soon as it hits this cold wall, it will condense back into liquid and drip back into the flask. And so you can keep on heating for a long time because you're not going to lose material by evaporation because it keeps condensing and dripping back down there. For heat, you can just write heat like that. You don't have to draw in a Bunsen burner or anything, any other kind of heater like that. You can just draw the heat source like that. So that's the apparatus. And then just a very brief description is that it avoids loss of material by evaporation. By material, it could be the unreacted starting material, it could be the product, it could just be the solvent. It depends on what your reaction is, but it avoids loss of material by evaporation, because anything that vaporizes condenses and drips back into the flask. That's the principle of how reflux works. Okay, so that's the method. So then it wanted you to suggest what reaction would actually happen when you do this prolonged heating with conch sulfuric acid. So you need to recognize this reaction, that this reagent dehydrates alcohols. So where you have an OH group, the conch sulfuric acid will take away the OH group and it will take away a hydrogen from the next door carbon. So in principle, in this case, there are two products. It says excess conch sulfuric, so both of the OHs are going to react. And what actually happens is this, which is that if you take this OH away, you take a hydrogen away from there, so they combine to give you a water and you get a double bond here. So an alkene group is formed, and then the same here. You take this OH group away and a hydrogen from there and you get another alkene group there, and you get two waters formed. So that was what it was really looking for. Some people proposed this, which in principle looks like it could work, because you could take away the OH from here and this hydrogen, because of course there's a hydrogen there, get a double bond there, and then this OH and that hydrogen and get one here. Again, plus two waters. Now the trouble with that is that that compound's going to be very unfavourable. So you're not going to get that, you're going to get this. So I didn't allow that, or I think I gave you 1 mark if you got the equation right, but not both marks. Arguably that was a bit mean, but you can see why you're not going to get that if you think about what you know about shapes of molecules. Okay, so this is just a reminder that anything that breaks the rules in shapes of molecules is going to give you a high energy state, which is likely to be less favourable. So if you think about it, this carbon has just got 2 regions of electron density around it, because it's got 1 double bond there and 1 double bond there, so it should be linear, and it's not. The bond angle actually there is 120 degrees, it's not linear. So that's going to be very unfavourable, because you're going to get big repulsion there, and so that's much less favourable than this would be, where the bond angles are basically 120 degrees, is exactly what it should be around a doubly bonded carbon like that. So that's what you get. You weren't a million miles away from that one, but make sure you can see why that's not going to be favourable really, and this is what you're actually going to get. And don't forget the 2 waters. Okay, each of the OH that goes takes a hydrogen with it, so that one gives you 1 water, that one gives you the second one. The equation must balance. Just because it's organic chemistry doesn't mean equations don't have to balance. Part D then addresses this sort of real world issue that when you've done an organic reaction in general, in your pot you don't have the pure organic product. You have hopefully your correct product, but it's going to be mixed up with the reagents, potentially other products you formed, the solvent, all kinds of stuff. And you need to know a little bit about the techniques that are available for purifying your product out from that mixture. So in this case, we've got this as our product. And the important feature that has is that it's non-polar. As you know, hydrocarbons are non-polar, so it's going to be insoluble in water. And that facilitates the use of a separating funnel. Okay, so you need to know about separating funnels. So a separating funnel looks like this. So you have this sort of bulb. It's a slightly asymmetric one, but you get the idea that you have this bulb here with a stem with a tap on it at the bottom, and then a stopper that can go in the top, like that. So that's a separating funnel, and that's the key to the first part of this purification. So you're going to have that, but you're going to have your conch sulfuric acid in your pot as well, because that was excess, so there's going to be some of that left over, and there's going to be some water which was formed in the reaction as well, so that's going to be there. And it's about getting this separate from these things, as well as from any other organic products that might have been formed in sort of side reactions and things. So the first step is neutralization, and you probably would dilute the mixture with water first, but you don't necessarily have to say that. But what you do have to say is that you add aqueous sodium carbonate to the reaction mixture. Sorry, that should be aqueous, that's important. Quite a lot of people just said add an alkali. You always need, in chemistry exams, to try and avoid saying things like that. Don't ever just say add an acid, add an alkali, add a salt, whatever. You've got to specify. There may be a choice, or there may be all sorts of ones that they would accept, but you've got to name one. And that's important, not just here, but it's a general principle in these how do you do this kind of questions. Sodium carbonate is better than sodium hydroxide. It doesn't actually matter in this case, really, but with some products which you'll meet next year, sodium hydroxide would actually destroy the product you'd made, and so sodium carbonate is used because it's a much sort of milder alkali. They probably would give you the marks for sodium hydroxide, but try and learn sodium carbonate to be on the safe side, and it needs to be aqueous because you want to have two distinct layers in your separating funnel. Okay, because the hydrocarbon product is insoluble in water, so you're going to get two layers. Now you don't know what the densities are. You can probably guess, oil usually floats on water, so the organic phase is probably on the top, the aqueous phase at the bottom, but it doesn't matter, because whichever way round, you can, once they're separated, you can release the lower phase, and then if you need to, separately release the upper phase and separate them out. But the important thing is that you do that in a separating funnel. And then shake so that the carbonate gets access to the acid in the mixture, and open tap in the inverted position. I don't know if you need to write all this detail, probably not, but it doesn't hurt. In the inverted position means that you hold the funnel upside down so that the tap's pointing upwards, and then you turn the tap and release the pressure, because obviously the carbonate's going to react and produce carbon dioxide gas, so you need to release that gas pressure. Okay, and then open the tap and release the phases separately. In reality, the organic phase would be the top one, so you would just leave it in there and just get rid of the aqueous phase at the bottom, but you can't necessarily know that, so this would be fine. So that's the first step. It then prompts you to say wash it. What does that mean? Well, it means that you should now have got rid of your acid, or most of it anyway, but of course you're going to have some sodium carbonate there, and there'll still be potentially other water-soluble things there as well, but mainly it's the sodium carbonate that you've now got to get rid of. So the second thing is washing, which just means that you repeat the process in the separating funnel using distilled water rather than the aqueous sodium carbonate. Okay, so that is important because otherwise you've got rid of your acid, but you've added a different contaminant because you won't be able to get rid of all the sodium carbonate, but you can do by washing it away. However, your products are still going to be wet. There's still going to be traces of water there. So the third step is drying. So you collect your organic phase in a conical flask. And you add a drying agent. Now again, a lot of people just said add an anhydrous substance, but they need you to make a suggestion. There are lots of possible things you could use, but it's got to be an anhydrous substance which is thirsty for water, so you need to know some examples. So the one or the two that are most commonly used are either anhydrous magnesium sulfate or anhydrous calcium chloride. Those are the ones that tend to come up in A-level examples. So let's just pick one of those. So add magnesium sulfate and specify that it's anhydrous. And what that will do is extract water from the mixture, and then it will tie it up in the solid because it ties it up as water or crystallization. So you've still got solid magnesium sulfate at the end, but it's now sucked all the water out from the reaction mixture, and then you can decant, which just means pour carefully the organic product into a clean flask. So those are essentially the sort of steps you need. So make sure you know about using sodium carbonate specifically as the best thing for neutralizing things, using a separating funnel provided your organic substance is insoluble in water. Obviously that won't work if it's soluble in water. Washing to get rid of the sodium carbonate, just again shaking up with water, allowing the sodium carbonate to go into the aqueous phase and then separating off the other phase, and then drying using an anhydrous substance, but name that substance. Anhydrous magnesium sulfate is probably the simplest one to learn. And at the end of that, you should have got rid of the inorganic contaminants because the sulfuric acid will now be gone, the water should be gone, but there may still be other organic things in there. If the reaction didn't go perfectly and you've got some other organic compounds formed, or maybe if you've got some unreacted starting material, that could still be there, and you've got to find a way to separate that, and that's where distillation comes in, which is the next bit. Okay, so we've got to draw a distillation apparatus, and it's the same principle as when we did the reflux apparatus. It's got to be a cross section, so you've got to show the continuous pathway that the vapour can go through. So again, we have either a round bottom flask or a pear shaped one. Let's do a round bottom one for a change, which looks like that, so we can label that. Again, conical won't do, it's got to be one or other of those. Your crude product means it's just not fully purified yet, goes in the bottom there, and again you're going to heat it from below. And then instead of putting the condenser vertically, you have a sort of adapter thing which goes in there. Again, make sure it's a tight connection so there are no gaps for the vapour to escape through there. And coming off the side here, at a bit of an angle, you're going to have a tube. Make sure it's angled downhill, because if you think about it, what you're going to get your vapour to do is to come up here, come down here and condense, and once it condenses and forms a liquid, it's got to travel downhill, because that's the way gravity will drag it. So if you have this pointing upwards, it's not going to work, it's going to roll the wrong way. So this has got to be pointing downhill. And then you usually have some kind of delivery tube on the end, which you can just draw like that. Now the top here has got to be closed off. You could just put a bung in it and that would be fine. Usually you put a thermometer there so that you know what the temperature is of the stuff that's boiling over, because you can relate that to the boiling point of the substance and check it's the right thing. So best thing to do is just draw a thermometer like that. But you must have a bung in the top. If you just have it open at the top, so if you had something that looked sort of like this, then obviously all that's going to happen when you heat it is that most of your vapour will go straight out the top, and you'll be waiting for your product down here, but you're not going to get any, or not very much anyway, because most of your vapour will just have escaped straight out of the top. So if this is closed here, your vapour has no choice but to come down this way, and so what we're going to do is put a condenser on here, so that as the vapour comes down here it hits a cold wall and turns into liquid. So again, you've got to make sure that you show that the cold water goes in and has to flow uphill. So let's just get rid of that label so we've got a bit more room here. So we'll put the cold water coming in there and out from there. They're very insistent on that, okay, that you have to have the water flowing the right way, because it doesn't work very well otherwise, and it's one of those practical things that they want to check that you know about. So the cold water flows in at the lower point and flows uphill like that, and it keeps this inner wall cold, so that as the hot vapour comes down here, it cools down, turns back into liquid, and the liquid will drip out from there, and you can draw some drops of liquid if you like to make the point, and of course you therefore need something to collect them in, so your product will be collected there. Okay, and that's fine for a distillation diagram. This needs labelling as condenser, but you don't need any more detail than that. So part F brings us on to percentage yield. So it tells us this reaction has an 84% yield and that we're starting with 14.5 grams of the diol. So you have to remember the definition of percentage yield, which is that it's the actual moles of product divided by the theoretical moles times 100. And lots of people decide that they can save a lot of time by not bothering with moles and just somehow using masses. In other words, they think, oh, if I just take 84% of that mass, that will give me the product, and that's garbage. Okay, because remember, the equation tells you that theoretically 1 mole of this should turn into 1 mole of that, but because these have different MRs, that doesn't mean that you'll get the same mass of this as you have of that, if you know, in the theoretical world. So if you don't turn into moles, you will get it wrong. So don't waste time thinking, oh, I can do this quicker by not bothering with moles, because you will just get nonsense if you do that. So if we just simply rearrange that, we can get that the percentage yield times the theoretical moles divided by 100 is equal to the actual moles. And you can either do that just by doing the usual thing, you know, sliding things diagonally from one side to the other, so theoretical moles slides from the bottom on the right hand side to the top on the left, and this goes from the top on the right down to the bottom on the left. Or you can just kind of think of it as 84% yield means that you actually get 84% of what you theoretically would have got, and that leads you to the same answer. So however you think of it, this is what you need to get. So that means, first of all, theoretical moles, remember, is going to be the same as the moles of this, because theoretically each mole of that should turn into a mole of that. So theoretical moles is actually just the moles of the dial. So we can get that the moles of this is mass over mR. Now you've got to be careful with the mR in these things. Make sure that you count the hydrogens correctly. So this is going to be C6, and if these were just hydrogens, it would be C6H12, remember, not 14, because the ring takes 2 hydrogens away, but you've got the 2 extra oxygens inserted as well. So it's C6H12O2, and if you add that lot up, you get 116. So it's our 14.5 grams divided by 116, which comes to 0.125 moles. Okay, so that's the moles of that, and that's equal to our theoretical moles of product. Okay, you can't do that directly with mass. You can't say theoretically 14.5 grams of reactant would give you 14.5 grams of product, because obviously some of the mass has been lost as water. That doesn't make any sense. That's why you have to turn it into moles. So that's the number we need. So we can just say that's equal to 84, which is our percentage yield, times 0.125 over 100, which comes to 0.105 moles. And now we're almost there, but all we have to do is turn that back into a mass. So we just get mass is equal to moles times mR, which is 0.105 times, and of course it's going to be a different mR, right, because we've lost 2 waters. So each water is 18, so we've lost 36 from that mass of 116, which means that the mass is actually just, the mR is just 80 for this product. So it's 0.105 times 80, which comes out to be 8.4 grams, and that's your answer. Okay, so make sure that you're confident about that, and really it's just about remembering you've got no choice, you can't take shortcuts, you've got to work in moles. So then in part G we get this infrared spectrum, and the question is whether it's consistent with having got the product that we expect. In other words, does this spectrum look like it fits this product, or might there still be some unreacted OH groups there? So we know what an alcohol OH should look like, because it tells you on your datasheet that it gives you a peak between 3,200 and 3,600 wave numbers. So we can just go looking for that. So that means that there should be a peak, and you know, you've seen lots of these. So 3,600 is here, 3,200 is sort of here, and what it means is that if there were unreacted OH groups, we should be seeing a peak that looks something like that, and you can see we really haven't. There's just nothing in that part of the spectrum. So we can be very confident that the alcohol OH groups are not there, but what you must write down is that there is no alcohol OH peak, and then you must quote the wave numbers. Whenever you're talking about infrared data, don't just say there's no alcohol OH peak, because they'll say, how do you know? You've got to say, yeah, because I know where to look. So you just quote the data sheet and say 3,200 to 3,600 wave numbers. So therefore you can be very confident that all the OH groups have reacted. Some people got confused by this, but remember that you always get a cluster of sharp peaks around 3000 wave numbers, and that's what that is. Those are the CHs. So you've really got to just look at lots of these infrared spectra so that you learn to recognize what peaks look like and don't just rely on the numbers. So those are the CH peaks, which of course you would expect to get here. One or two people also suggested that you might be seeing carboxylic acid OH peaks. But again, if you look at what the peak's expected to be for a carboxylic acid, it's 2,500 to 3,300. So in other words, if we just get rid of this, the range is going from there up to sort of here somewhere. So you should have an enormous wide peak. This bunch of sharp ones in the middle of that range, that's not what we're talking about. That range 2,500 to 3,300 really means that you have a peak spanning that range. So it looks kind of like this, and then you get the sharp peaks on the top, and then usually some sort of funny shape like that, but it's just a massive wide peak like that. So again, you have to practice lots of infrared. You can't just look at the data table and expect to be able to make sense of it. You need to have looked at enough spectra that you know that's what a carboxylic acid peak would look like, and this spectrum looks nothing like one. So the answer is yes, it's consistent with a hydrocarbon in the sense that there are no OH peaks. And then it says, what about this peak? This sharp peak around between 16 and 1700 wave numbers. Some people suggested it was a carbonyl peak, but again, what that comes down to is detail. So carbonyl peak is listed in your datasheet as 1630 to 1820. So it starts, in roughly the right place, but it should go all the way up to there. And it's a massive peak. So what you actually see for a carbonyl peak is something like that. Okay, it's a really strong peak, not just a little tiny sharp thing in the middle of that range. So again, it's about familiarity with the spectra and recognizing that doesn't look anything like a carbonyl peak. And of course you wouldn't expect a carbonyl peak from this product anyway, but if you did, you'd be worried because that doesn't look like a carbonyl peak. What it actually is a C double bond C peak. Okay, and we haven't talked about those very much, which is why the question was kind of hinting you've really got to look at your data sheet for this one. But it tells you C double bond C comes from about 1620 to 1680 wave number. So you can see it's a much narrower range than the carbonyl peak, only about 60 wave numbers, and that's consistent with it being this little sharp peak in the middle there.